Hi class, this video is on topic D4, Young's double slit experiment. Recall that interference is the phenomenon that occurs when two waves in the same medium interact. When two waves cross paths and become superimposed, they interact in different ways, constructively and deconstructively. And also recall the term coherent, a condition where two waves have the same frequency and fixed phases. Also recall the interference pattern for 2-point sources. If source 1 and source 2 are coherent, then symmetrical patterns spread out from the sources, producing line locations where constructive and destructive interference occurs. Just recall that the wave front in this case would be a circular wave front because they are point sources. And then the solid line represents a crest, the dotted line represents a trough. And when a crest meets a crest, that's where you have constructive interference. So we denote that with a closed circle. And when a crest and a trough meet, that's destructive interference or an open circle. Recall that a node is a place where full destructive interference occurs with zero amplitude. And so the crest and the trough have canceled each other out. There is zero displacement. Those points together form a curve, and those curves are called nodal lines. So if you connect all the nodes, then you get these nodal lines. And the nodal lines, what they actually look like if you had some water waves and you had a light, so you were projecting the patterns created by thicker areas of water and thinner areas of water. Those nodal lines would be distinctive patterns of, or less distinct patterns of sort of fuzzy gray lines, whereas the distinctive black and white areas would be the areas of constructive interference. So we can trace those gray fuzzy lines, those nodal lines, and we can take measurements on the nodal, based on the nodal lines. And we have 3 equations for taking measurements and then eventually calculating the wavelength when you have 2 coherent sources. So here's the first equation. It's based on the path length difference, the node line number, and the wavelength. Recall that we start numbering closest to the perpendicular bisector. So we have the line that connects the sources, then we cut that line in half and make it 90 degrees to the original horizon or horizontal line. And then the first nodal line that you see to either side is called n equals 1. So based on path length difference, we have this first equation. So that's the difference between this line, this green line, and this green line. We also have another equation that is based on the angle of the nth nodal line and the distance between the 2 sources. So this would be a good equation if we have the distance between the 2 sources and the angle, and we know which nodal line we're talking about, and we're solving for wavelength, or if we knew wavelength and we knew everything else, we could find the distance between these 2 sources. And we have a third equation, and if we are given the distance from the midpoint of the sources to the point of interest, and the perpendicular distance from the right bisector to the point. So just depending on what we're given, one of these 3 equations could be used to calculate wavelength of the coherent sources, among other things. So this is what the wave interference pattern looks like, the 2-point wave interference pattern for water waves. But a water wave is just an example of a mechanical wave. So recall that sound is also a mechanical wave. So let's say that these are 2 speakers. What would happen if you walk along the back of a room of 2 speakers that are that are projecting the exact same tone. These waves are in phase, so these waves are coherent. So what would happen? So pause this video and think, what would happen? Well, you're going to hear loud and dark and loud and dark as you reach an area of constructive interference, then destructive, constructive, destructive, constructive, destructive. So it's alternating loud and soft, because remember, in sound, amplitude is volume. So if there was just one note pelted out two speakers and they were in phase, you wouldn't hear different notes, but you would hear that note loud, that note soft, loud, soft, loud, soft. Destructive interference of sound means you don't hear sound at all, or you hear it more softly. Okay, and just one more thing to recall before we move on to Young's double slit experiment and the new stuff. What were the conditions required for this type of interference pattern? We had to have the two or more waves moving through different regions of space. The waves come together at a common point, and waves are coherent, same frequency, and phase difference is constant. So you should have just completed the wave or particle worksheet on light. And this is a major thing that's being investigated in this unit. Is light acting like a particle, or is it acting like a wave? And in previous years from grade 10 optics, you've talked about light as if it was a particle, always traveling straight lines. And you never really knew you didn't know anything about waves to question whether it did have wave properties. But the focus of grade 12 light unit is that light does have wave properties. So looking at the worksheet yesterday, you should know from that Newton's particle theory of light explained reflection, refraction, and rectilinear propagation of light. However, not diffraction. So on the other hand, Huygens' principle, which was based on light, the wave properties of light, Huygens' principle explains reflection, refraction, and diffraction of light. In the 1600s and 1700s, the debate over the nature of light, particle or wave, was in full swing. And at this point, if light travels as a wave, interference should occur. It should be able to be demonstrated if light is a wave. So unfortunately, the early attempts to show interference patterns with light, it just could not be seen like the water waves. You could not demonstrate it with light. And why not? The sources of light were out of phase, and the wavelength of light is very, very, very small. Recall that the wave-water interference patterns are so easily observed because the wavelengths are large and easy to measure. And remember that wavelengths are large when frequencies are small, because there's that inverse relationship according to the universal wave equation. So do you remember these where we were adjusting one variable in the little gizmo? When we increase the frequency, so from this diagram to this diagram, we increase the frequency, and we get more nodal lines, and there's almost so many that they're close together and we can't see them. So this would be more difficult to analyze as compared to this. And through the universal wave equation, if we have a constant medium, you have a constant speed. V equals F lambda. If speed is constant, that means a higher frequency. So higher frequency is also saying very low wavelength. So very large frequency is very small wavelength. Visible light only has 400 to 700 nanometer wavelength. And nanometer means times 10 to the minus 9. So with really small wavelengths, you get more of this. Many nodes that are hard to distinguish, they would be hard to measure, and you'd be hard pressed to see an interference pattern. And then also the distance between sources increases. That was also another thing that would make It would increase the nodal lines maybe to an extent that you can't read the results. So Thomas Young came along and successfully demonstrated the interference of light. This provided evidence for the wave-like nature of light, and the wave theory could explain all properties of light except its propagation through a vacuum. But that comes later in history, in physics history. So going back to those conditions for interference patterns, let's revisit it and check off how Thomas Young set up his experiment. So he's going to use 2 different slits and a screen to capture the interference pattern, and he's going to use a monochromatic source of light so that the 2 waves are coherent. So a monochromatic source, an example of it is a red laser. So monochromatic means composed of only one color or wavelength. So a laser is one way to accomplish that. So Young used diffraction through a double slit to create 2 sources from a single coherent source so that the 2 sources were close together and in phase. You can't just have 2 different lights. You can't have 2 different lasers or 2 different light bulbs because they won't be coherent. You could even have 2 identical lasers, but they won't be coherent and perfectly in phase. They'll just be the same wavelength. So if you start from one laser, shine it through a single slit, so you are reducing what light is there, and then that single slit you get diffraction. You send that resulting diffracted light into a double slit so that it appears as if you have 2 sources, and then you set up a viewing screen and you observing the interference pattern on the viewing screen. So this was really key in order to check off those conditions. And the results of his experiment produced a series of light and dark fringes on a screen placed in the path of the light with the pattern that resembled the results of the water wave interference in the ripple tank. So remember when I said you're walking across a room that has 2 speakers? So this is you have the interference pattern and you capture the light on a screen and you will see light, dark, light, dark, light, dark, light, dark, and obviously the middle is a lot brighter. The words are covered by my recording tools. So I just have to see what I'm looking at here. Oh yeah, interference fringe. So the definition is one of a series of alternating light and dark regions that result from the interference of waves. So we have a monochromatic source because we've used a laser through a double slit. So that's why it's called the double slit experiment. And then it looks like there's 2 wave sources because of diffraction here. And then the interference of those 2 waves, you get the nodal lines, which are the destructive areas, and then you get the constructive areas where the crests add. And then those constructive interferences end up on the screen as you're adding to the light, you're adding to the energy, so you get really bright, and they're labeled M equals 1, M equals 2, M equals 0 is in the middle, and then M equals 1, M equals 2. So let's talk about the bright lines. So those are called bright fringes. Those happen when there's constructive interference, and it's when there's a path length difference that is equal to a whole number of wavelengths. So if you kind of look at this as at an angle here, so they're traveling at a different angle, but somehow the crests have to line up. So the crests will line up if the path length difference is like 5 times wavelength, 20 times wavelength, so a whole number of wavelengths. So there's an equation, m number of wavelengths, there is a trigonometry right here. So if this is theta, through similar triangles, the theta is from the well, let's just go to the variables. The angle between the bright line to the center line. So if theta is the angle of the bright line to the center line, through similar triangles, you also get this triangle here. So the path length difference is from here to there, that delta L. That is equal to, so sine theta equals L over D, because that's the hypotenuse. The hypotenuse, this side, the opposite side over the hypotenuse, gives you sine theta, rearrange for L, and we have the difference in the path length is d sine theta. It's also equal to m lambda if we want it to be a bright fringe. So we have this new equation where d is the slit separation. Lambda is the wavelength of light. Those are both in meters. And theta is the angle of the bright line to the center line. And then m is going to be a whole number. I can't remember if 0 is a natural number. So it's going to be 0, 1, 2, 3, 4. And then depending on what we're given, we might not have theta. And so we might need a different way to write that equation. So we might have the distance from the mth bright fringe to the screen center, and we might have the distance to the screen. So this is L here, and this is X is the distance from that bright fringe to L. So that's L and X. And we might be given those values. You know, theta might be very small, but these two values are measurable. So depending on what we're given, we might want to use this version of the equation to solve for theta or X or D, depending on what you're looking for. So now the dark fringes, the textbook derives these equations, by the way. You can find those around page 480, and I encourage you to look at those to see if you understand the trigonometry that is based on these diagrams. So we talked about the bright lines. The dark lines also have equations. The locations of the dark lines are called minima. Oh, I forgot. The bright lines are called maxima. The dark fringes are called minima. And we've got a similar equation to the one for the bright fringes. It's d sine theta as well, but we have, instead of m, we have n minus a half lambda. And we also have another equation depending on whether or not the angle theta is available. So just taking a look at the similarities, I will mention that in your textbook, on page 484, there is an incorrect word which might be confusing. So on 484, in the summary, the second last bullet point of the summary, it says the nth order bright fringe is located at xn, but no. The n's are related to the dark fringes, the m's are related to the bright fringes. So cancel out, draw a line through bright and write dark. So there's an error in the textbook that the publishers have tried to communicate out there. So for the double slit experiment, you're going to use one of these four equations, and just depends on what's available. So let me do some examples and show you. Oh yeah, for the separation between adjacent fringes, so from bright line to bright line, we also have this equation here, the change in x. So the change in x from like m1 to m2, that would be the change in x, is L lambda over D, which that's equal to x1. So if you look at this, if you sub in 1, like the distance between M3 and M4 would be the same x as x1. So that's why these equations are the same thing. So for our first example, we have a red laser light with a wavelength of 658 nanometers passing through a double slit, and the third bright fringe is observed at an angle of 2.80 degrees. Determine the slit separation in millimeters, and how would the slit spacing compare if we used a blue light source? So just reading it over, what would be something to highlight and maybe record in your given section? So a red laser light, well, red is important, but we actually have the specific wavelength. So here's the first given, that's lambda, passes through a double slit. The third bright fringe, so third bright means m equals 3, is observed at an angle of 2.8, so that's theta. So setting up our problem, we have m, we have theta, we have lambda, and we are calculating small d. So this is the equation that connects all those things together, and we rearrange to solve for d, and we'd get 4.04 times 10 to the minus 2 meters. Oh, sorry, 4.04 times 10 to the minus 5 meters, which is 4.04 times 10 to the minus 2 millimeters. And then it says, how would the slit spacing compare if we used a blue light source? Blue light has a lower wavelength. So if we put in a lower number here, we're going to have a lower slit spacing. So for example 2, the two slits are separated by a distance of 0.050 mm. And a monochromatic beam of light with a wavelength of 656 nanometers falls on the slit and produces an interference pattern on a screen that is 2.6 meters from the slits. So looking at our get distance, we have a slit separation of 0.05 millimeters. So to go from millimeters to meters, you're going to do times 10 to the minus 3. So that's 0.05 times 10 to the minus 3, or you could just move your decimal 3 over because maybe you're familiar with it. And then we have a wavelength, so a lambda of 656 nanometers, so that means times 10 to the minus 9. So we have D and lambda, and we produce an interference pattern on a screen that is 2.6 meters from the slit, so that's L. So what equation would we have that does that? There's kind of a, not the neatest diagram, but ideally use a ruler. So this L is given, so that's a hint that we can only use this equation. We don't have theta, so we're going to sub in calculate the fringe separation at the center of this pattern in centimeters. Sorry for that brief interruption. That was just my cat getting dinner. Okay. So we were talking about this example, and you might wonder, what is M? So it says two slits are separated by a distance of 0.05 millimeters. A monochromatic beam of light with a wavelength of 656 nanometers falls on the slits and produces an interference pattern on the screen that is 2.6 meters from the slits. Calculate the fringe separation. So fringe separation, that is referring to from one bright line to the next. We don't care which one we're talking about. So there's not really one M in particular, but the easiest solution would be to say M equals 0 to M equals 1 would be X1. So if we sub in M1, and we're solving for X1, then we can just use that simpler equation. Another option would be to sub in X4, M equals 4, and then do it again for for M equals 3, and then do the subtraction of those answers, but that would be a long way to do it. You could just do it in one step. So delta X would be L lambda over D. Notice the conversion to meters. So notice you should be getting lots of practice in converting with nanometers because of wavelength of light being so small, and millimeters because of the slit widths being so small. Anyways, we get 0.034 meters or 3.4 millimeters. And in the second part, it says what would happen to the fringe separation if the screen was placed further. So if we increase L, then we're going to increase delta X. So an extension question, in these examples, we weren't solving for wavelength, but that's a very common way that this is applied, using the double slit experiment to actually find the wavelength of light, because it is so small and difficult to measure. So we measure it indirectly through these experiments like this. So what would we need? Let's say we have a helium neon laser light. Let's determine the frequency of the laser light. So I want you to think of, how could you determine this? What would your experimental setup look like? So that's just an experiment. That's an extension question for you to think about, because that's actually testing if you understand this section. And if you don't, I encourage you to reread this section and the one with the water waves. Also, an activity that we sometimes do is determining the wavelength of the waves using each of those three equations from the water waves lesson. So if this is a bird's eye view picture of two water waves, or a representation of two sound waves, can you tell the wavelength of the original coherent sources? So I'm going to post something else about that for you to practice doing that, because that would give you practice on those three equations. So it's time for you to practice. Submit this exit ticket for this lesson and practice questions, complete them and submit them. Hope you have a great day. Stay safe.